Alright, welcome back. So today we're going to solve a problem that involves the work in lifting a chain. So in this problem we have a chain of density 400 grams per meter, and it's hanging over a building. So you can kind of see that illustrated down in the picture. It's this region down there, and at the bottom of it is a hook that weighs 20 kilograms, quite heavy. And this is all hanging down a distance of 30 meters. So the question is, how much work is required to lift the hook up to the roof? And I guess what's implicit there by pulling the chain up. Pulling up the chain. Right, so you can imagine you're standing on the roof and you've got to drag the chain up. How much work would that take? And so we're going to have to split this into two pieces. There's the work to lift the chain, and there's the work to lift the hook, right? Because the hook is at the bottom, and it has to come sort of all the way up. And so if we split this problem into a few pieces, the work to lift the chain, this is like the ones we've done in class, this will do by using an integral. And the reason for that is that every little part of this chain behaves very differently. The stuff near the top travels a really short distance, and the stuff near the bottom of the chain has to go, as close to as much as 30 meters. And so to keep track of those different things, that's where the integral really comes in. However, the work to lift the hook, well, this is pretty easy. We can just do it. We can just kind of do it now, right? So that work is just going to be force times distance, because that hook is just 20 kilogram mass, and so that force is going to be 20 kilograms times 9.8 meters per second squared. It's our force, and then that whole force, that whole weight, is going to be going up a distance of 30 meters. So that's going to be our distance. And so if I multiply those things together, let's see what I get. I'm going to get 30 times 20 times 9.8. I get 5880. So I get 5880. And I check my units, kilograms, meters per second squared, meters. That's going to be Newton meters or joules. Okay. So the work to lift that hook is just gotten by multiplying those two numbers together. Okay. Now the work to lift the chain, that's going to be a little bit more challenging. Right. So let's make some more paper and kind of see how we would do that. Right. So now if we want to lift the chain, the idea is that we want to look at a small piece of the chain, say this piece here. So it's going to be a distance of x meters from the top. I'm getting rid of that. And we imagine that it has kind of a thickness or a length delta x. So let me write that down here. So take a piece of chain of length delta x meters, and it will travel a distance of x meters. Right, so it's going to go up this x distance here to get up to the top, and the length of that little piece is delta x. Right? So let's figure out how to do that. So the work is going to be force times distance, and so in this case that's going to be mass times 9.8 meters per second squared times x meters. Okay. Notice I'm writing the word meters just so we don't have an m to confuse with mass. And so now all we have to do is we have to figure out how to get that mass, right? And so now if I think about how I could get mass, maybe I'll do that down here. Mass is going to be length, which again I think of being measured in meters, times our conversion factor, which we have up here, that 1 meter of our rope is going to weigh 400 grams, right? And so we may want to just rewrite that as 0.4 kilograms per meter. And so if I think of my length as being measured in meters, then if I multiply 1 meter by 0.4 kilograms, then that will give me my mass. Right? And so we go back and we say, well, what was the length of our chain? Well, it had length delta x meters. And so if I put that information in here, I'm going to get delta x meters times 0.4 kilograms per meter. Then I have 9.8 meters per second squared times x meters. And at the end of the day, when we put all these numbers together, what we're going to have, let's see, the meters cancel. We're going to get kilogram times meters per second squared times meters. So that's going to be joules. So I'll put that unit there. And once we kind of combine everything, I guess we have 0.4 times 9.8. Let's see what that is. 0.4 times 9.8 is 3.92. So we're going to get 3.92 x times delta x joules. And so our total work on the chain is going to be the integral from 0 to 30. Because remember, this strip could be in any position, so we want to add up all of the strips as x goes from 0 to 30 of this work. So we're going to get 3.92 x dx. Remember that delta x often, almost always, becomes dx when we rewrite it in terms of an integral. And now I can just take this quantity here and feed that into Desmos and see what I get. So it's 3.92. So integral, let's see if I can do this. Integral int from 0 to 30 of 3.92 times x dx. And it's telling me that the answer is 1764. And let's put that answer here. It's in red. What did it say? 1764. Let's double check. Yes, 1764 joules. And so our final answer, total work, so this is chain plus the hook, is going to equal the sum of those two numbers, 5880 joules plus 1764 joules, which, if we add them all together, is going to be 7, 6, 4 joules. Okay. And we could go and do kind of a reality check if you wanted with this problem. Something I like to do is to see whether my numbers make sense. For instance, I got that it was a lot less work to do the chain. It was only 1764 as opposed to 5880 to lift that hook. Does that seem right? And I think it does, right? That hook's really heavy. It's heavier than the chain, and it has to go the longest distance. It has to go longer than any link in that chain. So I think that seems pretty reasonable. And I think this problem shows a lot of the little subtleties that you may need, converting from grams to kilograms, having an extra weight on the bottom can be important as well. So thank you for watching, and we